Hello everyone. As Java developers, we are always curious about the memory footprint of our Java objects. In today's adventure, we will try to explore how Java objects are structured in heap memory, the amount of memory they consume, and how the JVM uses a 32-bit pointer to represent 64-bit memory addresses. Understanding memory layout will help us to optimize our Java applications. These are the topics we will be discussing today. Java library, Java object layout. This is the key that will unlock the door to everything we are going to discuss today. The second one is ordinary object pointer, then object header. After that, we will discuss alignment and padding, then compressed ops, and at last, we will see some practices for memory optimization. Before we dive in, let's clarify that the concepts I will try to explain are specific to the OpenJDK HotSpot JVM. Memory management can vary between JVM implementations because the Java virtual machine specification does not mandate specific memory layout requirements. We'll keep things simple and focus on understanding the core concepts. You can find links to all the resources I used in the description. Let's start with Java Object Layout library. It's a tiny toolbox provided by OpenJDK team, and we need to add this dependency in our class path. This library relies entirely on Java's unsafe and reflection APIs for its operations. I have created one class memory layout test. My class having one long and integer field. Mind class having one integer field. Integer wrapper class. Mind instance. Int array and byte array having one element and boolean wrapper type. Virtual machine, this is the interface provided by OpenJDK team, and this is the implementation of this interface, and this is size of method which will print the size of Java object. Let's run this size of method and see what will be the output. So this is the output. So to understand why the size of integer wrapper object is 16 bytes, mind is 16 bytes, integer array and byte array 24 bytes, and boolean is 16 bytes. First, we need to understand ordinary object pointers and object headers. Let's try to understand what is OOP, ordinary object pointer. So an ordinary object pointer in Hotspot JVM is a managed pointer to an object, or we can say they are references used to locate Java object inside heap memory. Typically, an OOP is the same size as a native machine pointer, 32-bit or 64-bit according to the system architecture. OOP is called a managed pointer because the JVM is responsible for the entire object lifecycle. For example, object obj equals to new object and mind mi equals to new mind. We know these variables as reference variables. So we can say ops are the low-level representation of these reference variables used internally by the JVM. In a simplified manner, reference variables can be considered as ops. Let's see what is object headers. So suppose this is the heap. We can say all Java objects in the heap have an extra bit of information at the beginning called an object header, or we can say कि it's a block of memory which stores metadata about the object. Suppose this is the object, so this is the header. It means the object not only contains the instance field, they also have some extra information which is known as header, and this ops will refer to this, not only the instance fields or the object. So the ops will refer to this whole structure in heap. And object header consists of mark word and class word. Let's see the description of object headers OpenJDK implementation. So this is ops description. This is a header file and it contains one mark word and one metadata which have one class pointer, and there is also one compressed class which we will discuss later in this video. Header contains two things, one mark word and the second one is class word. So let's see what is mark word. So the mark word is used to store identity hash code, object logging information and GC metadata. The size of mark word depends on the architecture. It is typically 4 bytes in 32-bit system and 8 bytes in 64-bit systems. Let's see the OpenJDK implementation of mark word. So this is a header file, mark word. .hpp. So for 64-bit system, 25 bits are unused and 31 bits to store the hash code of any Java object. Unused gap 1, age 4, this is for GC. Unused gap 1 and lock 2, so 2 bits for locking information, and it contains only one unsigned integer pointer. That's why it is dependent on system architecture for 4 bytes or 8 bytes. This is Git repo for Java Object Layout Library, and there are a lot of examples. You can check how markword stores different information. Let's see what is class word or class pointer. It's a pointer to class metadata such as class name, its modifiers, constructor, field, superclass info, and so on. It's a 4 byte in size. This metadata resides in the method area, which we can access at runtime using class object. Let's print the class layout of my class, which contains 2 instance fields, long and integer type. We can see 8 bytes for mark word, this is size, this is offset, and for this is description and the value. So 8 bytes for mark word, 4 bytes for class pointer, 4 bytes for integer field, and 8 bytes for long field. And these are the offset. Offset means how far they are from the base address of the object. We'll see the use of the offset. So suppose we have an object m inside heap. So when we call m.ln or m.getln, means any getter method, how does the JVM knows where the memory is allocated for these instance fields? Because the memory is allocated for the whole object, not for individual fields. Now the class pointer comes into the picture. Using the class pointer, the JVM gets the offset for that fields. Offset means these 12, 8, 16, 0, and adds these values to the base address of the object in the heap, and then fetches the address. So if m equals to my class, so this object.ln equals to address of m, means the address of object, means base address, plus offset of that particular field 12. So it will add that offset value and fetches the field data. And one thing is to note, in case of arrays, 4 extra bytes are used to store the array length. So if in our class, if there is any array, so 4 extra bytes is used to store that particular array length. So due to this object header, every Java object requires an additional 12 bytes of memory. So one information from the OpenJDK site, they are working on a project Lilliput, which aims to reduce the size of object headers from 128 bits to 64 bits. We can check out the examples in the Joel GitHub repository to see how Java headers contains different information. Let's see what is alignment and padding. In JVM, objects are typically aligned on 8 byte boundaries. This means that the size of every object is a multiple of 8 bytes. We can change it using this flag, something ObjectAlignmentInBytes equals to alignment. So the alignment value should be a power of 2 and must be within the range of 8 and 256. If the size of a Java object is not a multiple of 8 bytes, the JVM will add some extra bytes as padding to align it to the nearest multiple of 8 bytes. Now we can express the total memory reserved for Java object as size of any Java object headers plus instance fields plus 4 bytes for array length and plus padding if the object size is not multiple of 8 bytes. So mark word plus class word plus array length plus sum of all instance variables plus padding required. Let's run one more example and try to understand what we have discussed so far. So this is VM mode, 64-bit JVM, compressed references and compressed class pointer. We will discuss it after this. And this is object alignment 8 bytes, which we have discussed. And this is field size. References are 4 bytes in size. Boolean are 1 byte in size. Bytes 1, char and short 2, int, float, we know that also we know. And for array element, same, means if these are the element of array, the size will be the same. And this is array base offset, 16, 16, 16, 16. So let's see how this value comes. So array base offset equals to 12 bytes for headers, as we know, 4 bytes for array length, so 16 bytes. So but what is this 16 actually? 16 offset. So An array base offset is the starting point within an object's memory allocation where the array data begins. It's essentially the number of bytes we need to skip from the beginning of the object to reach the first element of the array. So it means 16 is the offset of the first element in the array. So suppose we have a heap where an array is stored. From here the array is stored from this location, and this is headers, this is for array length, so this is 12, this is 4, 16. So from there the first element will come, so that's why it is 16 bytes offset. Now let's try to understand what are compressed ops or compressed references. They are the real hero. So compressed ordinary object pointers is a memory optimization technique used by JVM to reduce the memory footprint of object references on 64-bit system. So they are used in 64-bit machines. Normally object references on 64-bit machine are 64-bit pointers, means they are 8 bytes in size. Compressed ops represent these references at 32-bit values. So instead of 64-bit values, JVM will use only 32-bit, which will reduce the memory consumption. This allows the JVM to efficiently addresses heap larger than 4 GB while still using 32-bit references, means maximum we can use 32 GB, because we know that 2 to the power 32 means in 32-bit system we can address maximum 4 GB of heap, but using compressed ops we are able to achieve heap size maximum to 32 GB. So by default compressed ops are enabled if the heap size is less than 32 GB. In this way the use of compressed references results in a 50% reduction in the memory consumption by OOP. If compressed ops are disabled, so it means we are using default ordinary object pointers which will take 8 bytes instead of 4 bytes. We can use these JVM flags to enable or disable. Use compressed ops and plus minus to enable or disable. If maximum heap size exceeds 32 GB, the JVM will automatically stops using compressed ops. So as in previous example we have seen compressed references equals to 3-bit shift. It means compressed references are enabled by default. And the same is class pointer. We know that the class pointer are 4 bytes in size. So if the JVM uses the compressed references for class pointer, so it will show here. But in this case this is 0-bit shift. It means class pointer are not enabled for compressed types. Let's see this flag value. One thing we can see, object alignment bytes 8 bytes, which is default set. This one, use compressed ops, the value is true, so default enabled. As we see, if compressed ops are enabled, so the size of references are 4 bytes. Let's try to disable this and see what will be the output. Yes, now we can see compressed references disabled, and the field size, the reference type are 8 bytes in size. So we can see that it will consume double the size of compressed references. What is base address? In a 64-bit JVM process, upon startup, the JVM will initiate a request to operating system for a base address, and this base address serves as the starting point for allocating memory for the Java heap. So this location or this address is known as base address because from this location the heap is allocated for Java process. Native address. 64-bit memory address of an object inside heap is known as native address. This is the actual address. Offset. An offset is a smaller compressed representation of an object's memory address. Instead of storing the full 64-bit address of a Java object inside ops, the JVM stores this offset. Now 32-bit versus 64-bit pointers. A 64-bit pointer unlocks the ability to address an enormous amount of memory, which is to the power 34 GB, which is far more than we can use at the present time. Downside of 64-bit pointers: increases memory footprint and decreases the cache efficiency. In contrast, 32-bit pointers limit us to use 2 to the power 32 bytes or 4 GB of addressable memory, which is insufficient for today's software need. Now let's see how compressed ops allow us to use 32-bit pointers to refer more than 4 GB of heap space on 64-bit machine. The important thing to note first is the heap size limit is calculated as 4 GB object alignment bytes. This can be checked into Java commands documentation. So they have mentioned the heap size limit in byte is 4 GB into object alignment in bytes. So it means as the default alignment is 8 bytes, so we can refer up to 32 GB of heap. Now let's see how compressed ops allow us to use 32-bit pointers to refer more than 4 GB of heap. As we know, JVM introduces padding to ensure that objects are 8-byte aligned. As a result, the last 3 bits of ops are always 0 because multiple of 8 in binary always end in 3 zeros. If we right shift by 3 bits, means we can remove those 3 bits. We effectively gain 3 additional significant bits, allowing us to store larger range of addressable value within 32 bits. Suppose this is a actual address and last 3 bits are 0, so we can remove these 3 bits and 3 more significant bit can take place here. So now this 32-bit pointer can refer more heap size. So we can say that actually we have increased the size of 32-bit pointer to 35 bits by removing 3 zeros or least significant bits. And second explanation is, as a 32-bit pointer we can hold 2 to the power 32 different values, roughly 4 billion. This translates to 4 billion possible offsets for object references. However, since Java objects are 8-byte aligned, the size of every object is a multiple of 8 bytes, assuming objects are maximum 8 bytes. As we know, every object is at least 16 bytes due to the internal overhead associated with object headers. But we are assuming the maximum size of Java object is 8 bytes. So in this way, 4 billion objects into 8 bytes, which comes to 32 GB. So this way, using CompressedOops, we can refer to 32 GB heap size. Now let's see compressed pointers beyond 32 GB. Compressed pointer can still be used even with the heap exceeding 32 GB, while the default object alignment is 8 byte. This can be adjusted using the ObjectAlignmentInBytes flag. The new value must be a power of 2 within the range 8 and 256. For example, when the object alignment is set to 16 bytes, means every object should be a multiple of 16. Compressed pointers can be used effectively with heap space up to 64 GB. It's important to note, however, as the alignment value increases, the unused space between objects might also increase. As a result, using compressed pointers with very large heap sizes might not provide significant benefits. Now at last, let's see some practices for memory optimizations. It is estimated that 30 to 90% of memory is wasted due to inefficient programming. If you don't write memory efficient code, Java will consume excessive memory, which puts pressure on garbage collection, increases application latency and reduces overall performance. Here are some coding practices to reduce memory footprint. Since each Java object has 12 bytes of memory overhead, it is important to choose data type in our class wisely. Whenever possible, use primitive data types instead of their corresponding wrapper classes. If you need to return an empty collection or map, prefer using collection.emptyListSetMap method. Same for single element collection, always use singleton-list-set-map method. Always specify the initial capacity and load factor when you know the collection and map size in advance. Replace boolean array with bit set and don't use p.split. Instead of create pattern and then use p.split. If possible, go for newer version of Java, as newer version are more optimized for overall JVM performance. Friends, I will share this document with you all so you can go through. So achieving optimal performance demands careful consideration of latency, throughput, and memory and CPU footprint, as improvement in one area often comes at the expense of the others. Balancing these factors depends on the specific requirement and constraints of our applications. Alright dosto, that's all we have for today's adventure. This whole JVM memory layout is complex. I am still learning, so I might not have everything perfect. But I hope you have understood the main ideas from what we have discussed. And finally, I will leave you with this thought. Let this inspire you to make a positive impact. Thank you for your time and attention. See you soon. Until then, keep learning and take care.